I wanted to go through a number of different things, just give you a little bit of the history and biology of it, move on into the experimental design, the statistical analysis aspects of it, and then move over into how the Ames test is, some of the biological issues it's used in, and where the statistics can become an influence in it, and then just pick up some of the new developments and conclude. So that's just a little bit of history. The Ames test started back in 1973 when Bruce Ames, the person on the right-hand side, developed this test, taking into account both the bacteria, but also some metabolic activation system. It didn't just spring out of nothing, and in fact, it could easily have been called the Malling test, because Heinrich Malling, who worked at National Institute of Environmental Health Sciences, and I worked for briefly in his department, actually did the key piece of work, which was to use liver microsomes, or mashed up mouse liver, to metabolize a compound called dimethyl nitrosamine, which isn't normally mutagenic, but once metabolized does become so. So Heinrich laid the beginning of the Ames test, but Bruce Ames developed it and made it widely available. It's become a sort of the workhorse of genetic toxicology. A little slide showing that it peaked in about in the region of 500 or more papers a year in the 1980s, down still to a healthy sort of 200 a year at present times. And there's estimated to be over 10,000 publications using it, and over 100,000 chemicals where there's data from them actually in the public record, but a lot more in the in industry records everywhere. There's an OECD guideline which was last revised, you'll see, over 20 years ago. It wasn't changed the last time that the OECD looked at it, although there is some discussion about moving forward, and it gets called the bacterial reverse mutation test. And the next slide, I'm just checking everyone can see these okay. I'll just get a feedback from people. You can see that okay on the screen?
Yeah.
Absolutely, David.
Good.
Absolutely.
Okay, well, just an illustration of the Ames test in practice. There's a Petri dish with agar put in it, and there's some bacteria which have been deliberately chosen because they're unable to grow in the presence of it, in the absence of the amino acid histidine. So on the left-hand side, you'd see a control plate, which a large number of bacteria have been put on there, together with some mashed up liver, which creates a metabolizing system, and the chemical of interest onto the agar plate. Majority of the bacteria don't thrive, eventually die out. A small number of them have a mutation, which causes them so that it can actually grow in the absence of histidine, and they'll form a colony. So the white patches are colony from a mutant bacteria, and the one on the right hand side is from a positive control where there's been a known genotoxic chemical has been added, and very large number of mutations have been produced, and that sort of forms the basis of the test. Plates are counted, plates are produced, and the number of revertant colonies are counted in each of the different treatment groups, and the results assessed. The actual Ames test actually consists of the full test involves 5 different strains of either Salmonella typhimurium or E. coli, each of which has a slightly different properties in terms of the chemicals that they detect, the type of mutations they detect. So the standard OECD guideline is for five strains. And in the guidelines, you'll see that it expects that at least 5 different concentrations should be used with a half-log interval between them, and that the concurrent negative and positive, perhaps even solvent or vehicle controls, are produced in each assay, and that you get triplicate plating at each dose level. So the actual experiment works out at about as 5 strains plus or minus this metabolic mix of mouse or rat liver microsomes. So it's equivalent, rather than a single experiment, to 10 mini experiments with between 6 and 9 concentrations, 3 reps per concentration, with between 180 to 300 plates being scored in each experiment or each Ames test. And the estimated cost, just from a quick look on the internet, of people offering to do it for between 1,500 and 4,000 euros per sample of chemical, depending on the number of strains, etc. On the statistical analysis side, the OECD suggests that the data should be presented as the number of revertant colonies per plate, and that the individual plate counts, the mean number and the standard deviation should be presented for each test concentration, positive and negative. So that's just a descriptive type statistics. For the evaluation and interpretation of the results, there's a statement that they want to see for a positive result, they want to see a concentrated related increase over the range tested, and a reproducible increase in one or more concentrations in the number of colonies in at least one strain, either with the S9 or without the S9. And the next couple of sentences are probably the key ones, and I'll put them on next there. So there's a very key statement, is that biological relevance of the results should be considered first, followed by the statement that statistical methods may be used as an aid in evaluating the test results. However, statistical significance should not be the only determining factor for a positive response. And they give a reference to, for the statistical methods, which is a paper or a chapter by Gary Mahon back in 1989, which was in the book about the statistical evaluation of mutagenicity tests that David Kirkland edited in 1989, and just a picture of, there was a number of UChem's procedures, the procedures in one book, and suggested statistical evaluations in another book. And so the very key point here is that there's almost a two-step phase, that the biological relevance, in a sense, overrides the statistical methods. So the statistical methods are really just for helping to aid rather than to making a decision, and they certainly shouldn't be the only determining factor. Probably because of Gary Mahon's book, one of the suggested methods for analysing the Ames test in that chapter was a analysis after square root transformation using a one-way analysis of variance, followed by Dunnett's test for the multiple comparisons. And you'll see quite a few of the people keeping to the OECD guidelines will at least try to analyse that using those methods. So that's it. A number of people in the past have looked at the methods for statistical analyses. There's a number of previous reviews. I've just mentioned Gary Mahon and others from the UChems who also reviewed some of the methods. Jochen Vollmer and Lutz Elder did a review of methods, of the methods that are available in I think it was a symposium that Ludwig Hawthorne ran in the early 90s, and they actually listed about 32 different methods and split them into those that involved significance testing, non-parametric analyses, methods based upon regression, and specific studies aimed at interaction between two or more chemicals or types of procedures. Dr. Edler also produced a review of statistical methods for genetic toxicology in general in about 1992. And then the last real, I suppose, one that called it a review was a paper by Byung-Soo Kim and Barry Margolin in 1990 in mutation research. And I just want to go forward a slide just to mention that Barry Margolin was a very key person, the developer of statistical methods in the Ames test in the 1980s and then 1990s. He worked at the National Institute of Environmental Health Sciences in the States and was very much involved with the people involved in the genetic toxicology. And he was very keen to try and impose or to try and to bring some statistical and mathematical thinking, statistical and mathematical models into the Ames test. Sadly, Barry, having moved to Chapel Hill, he developed a sort of chronic illness which severely curtailed his work in the sort of later life, and he died unfortunately tragically young a few years ago, but a very key person in the statistics community in this area. And you can see that one of the papers I've mentioned there is his paper with Norman Kaplan and Errol Zeiger, where he first, back in 1981, so only about 6 or 7 years after the Ames test had been introduced, that he actually tried to develop some mathematical modeling, statistical modeling of the Ames test. Just go down and just something from the Young-Soo Kim and Barry Magelin's review. Barry developed some mathematical models to look at and statistical models to look at the Ames test, particularly to take into account that some of the dose-response relationships were very non-monotonic. They would rise while the mutations were growing, were increasing dose levels, and then toxicity would kick in and the mutation rate would apparently fall because there are just far fewer bacteria there to mutate. And he developed some models which other people adapted for various reasons and purposes, but he carried on working on some of the modeling for some time. So the model that he developed really was one which essentially modeled the dose at the number of mutations at a particular dose by the background level, taking into account the dose, the mutation, the beta-1 model, or the B1 model, and taking into account also toxicity, and provided a test for the goodness of fit and a test for the mutagenicity of the compound. It's interesting that in this paper, Barry talks about the problem that the genetic toxicologists had in finding a way of being able to interpret the dose-response relationship in these complex curved responses, and how they really found it very difficult to use the modeling to make their decisions, which may explain some of the future way that it developed. But this, I guess, was probably where Barry, in a sense, left it and moved on to other things. But he provided a solid background for a potentially a biologically based modeling approach to the data sets. This is a set of data that I use from time to time when I'm talking both to genetic toxicologists and statisticians, and it's a very good illustration of the difference between statistical significance and biological importance, and that argument that was, or the tension that was in the OECD guidelines about biology comes first and statistics can aid in the interpretation. This is some data from a very early on in one of the collaborative studies where somebody looked at vitamin C, ascorbic acid, in the Ames test. They did a pretty standard test. This is the TA100 salmonella strain without S9 mix, so nothing to added to improve metabolism. 5 dose levels, quite high concentrations at the end, the top level, perhaps the maximum now obtained, now allowed. 4 replicates at each level, which is 3 more. This is 1 more than the standard needs to be. And as you can see, there's a fairly consistent increase in the number of revertants with the increasing dose levels, concentration levels. And if you did a standard analysis of variance and pulled out the linear component, very, very highly significant dose-response relationship. And most of the people who are statisticians and they see this data say, well, that's a pretty clear-cut answer, a very clear linear dose-response relationship, that must be a positive. On the other hand, when the biologist looks at this, they say, or the geneticologist looks at this, they say, oh no, that's a negative. No evidence of biologically unimportant result. because they're basing it on what they call the twofold rule, which is that although there's an increase, highly significant increase, and it occurs probably that by a Dunnett's test at the top 4 concentrations are significantly different from the control, so it meets many of the criteria. The genetic toxicologists say we don't take a positive result until there's been at least a twofold increase over the background level, and in this 1.4-fold level. So this is the area where the between statistical significance and viral importance, where there's sort of contrasting views. Sometimes you get a genetic toxicologist who will say, well, that's just the sort of thing you statisticians will find. It's one of those very freak results that just by chance alone. But I'd always argue that actually this indicates that something's been going on in this experiment. It may be that vitamin C isn't a mutagen. Could be that it's some sort of artifact of the high concentrations that are used. Or alternatively, another possibility is that this is there wasn't any information about where the ascorbic acid came from, but perhaps it was a particular batch that actually was contaminated with a genotoxic contaminant, and what's been detected here is the genotoxicity of another chemical. But certainly indicates that something happened in that experiment, even if the biologists or the genetic toxicologists doesn't think it's important in genetic toxicology terms. Another point is that and always to go to the data, and there was actually over dispersion. This particular set of data, rather like one or two others, is quite interesting because actually there's more of an evidence of under dispersion. The data, the revertant counts look rather more similar within the groups than you'd expect from a poisson, and whether that indicates some sort of technical problem in the development of the test, I don't know. But it's not unusual to see actually more under dispersion in some of these Poisson distributions in the Ames test. I'm not quite sure why that comes about. So that's a sort of illustration of the contrast between statistical significance and biological importance, and it brings up this argument about the twofold rule. And this may well have originated because of something called the doubling dose in radiation, where there was a attempt, or used in the sort of radiation studies, to find a dose that doubled the incidence of particular types of genetic outcomes. So in human population studies, doubling dose that caused the proportion of untoward pregnancies to double, or childhood mortality to double, and then that would be the dose in the studies from the A-bomb survivors that actually appear to be related to these sorts of increases. It may be that that's not clear, but it may be that some of the genetic toxicologists, having worked in the radiation area to start with, like the idea of a twofold increase. So some of the test criteria that have come up are that you can find in the literature are that the number of revertant colonies should be at least twice the concurrent solvent control. In fact, for the TA100, which we looked at just now, they suggested they're 1.5 times, but still would have the results there would still have been below that, because the fold change is about 1.4, and that there should be some sort of evidence of a positive dose relationship in 2 separate experiments, either with S9 there or not. And then there's another one that Kim and Margolin noted that some of the strains, the spontaneous background rates are quite small, and for these they suggest there might be a 3-fold rule is appropriate. But as Barry Margolin noted, that back in 1999, quite a few people were beginning to wonder what the 2-fold rule really was doing and how valid it was. And Neil Cariello and Walter Pirgosh had a look at that, and one of the conclusions they drew that both for the Poisson model and for an over-dispersion, a negative binomial model, they suggested that the twofold rule was would actually produce more false positives when the spontaneous reversion frequency was low, and that it would also produce a lot more false negatives when the spontaneous reversion frequency is high. So they were suggesting there were some considerable uncertainties introduced by the use of this rule. And they pointed out the work of Hamada et al. 4 or 5 years before, who did a looked at the type 1 error theoretically for background levels of 5 to 100, and showed that in a two-group Poisson, that instead of 5% type 1 error, it was about an 8.4, and when for taking the multiple comparison, well, the multiple group comparisons up to about 20%. But as the negative control incidence increased, then you got the false negative results with very, very low type 1 alpha values, and similarly even with the negative binomial. So pointing out that just using these fold rules with low background levels, you may fail to pick up genotoxic chemicals, and with high background levels, you may produce. Sorry, with low background levels, you would possibly apparently pick up more genotoxic chemicals, and with high background level, you'd miss quite a few of them. So that was the situation probably, or even now, and David Gatehouse, who did quite a work on the Ames test, produced a sort of chapter in one of the standard genetic toxicology textbooks a few years ago, and probably what he says probably sums up the sort of the pattern of how data is handled at the moment in the field. He said that sort of several statistical approaches have been applied to results of these assays, and all have their strengths and weaknesses. I sense that is probably a statement more by the genetic toxicologists, who find that different methods give them different, sometimes give them different significance levels. They don't necessarily give the same result when there isn't a strong, highly potent genotoxin. So the fact that they're measuring the uncertainty in some of the measures is considered to be a weakness for a group that want to have a plus or minus result. He then says another approach has been widely used is to set a minimum fold increase, usually the 2 or 3 fold over the solvent control. And then the sort of what looks like an algorithm but actually isn't, that in general positive results should be statistically significant, dose related and reproducible, but without actually a clearly defined algorithm for that. So the situation, I've tried to capture it in a diagram, is that you have an experiment where you have a fold change, which is your criteria for positive results, which is measured on a particular in a particular experiment, and anything falls to the right of it is a positive and genotoxic. Anything to the left is negative and non-genotoxic. But of course, this value is very variable on your experimental design, on all sorts of other factors, and can shift backwards and forwards. So sometimes you'll have chemicals which are here but would be considered negative, or here which are negative, which would be, in some cases we call negative but would be called positive. So you've got a considerable degree of uncertainty in making these dichotomous decisions. And it's not just whether there might be a cutoff, a threshold value where above here you say definitely genotoxic, definitely non-genotoxic. There's also the issue that clearly, particularly for genotoxins, there's expected to be at least some sort of dose response to quite low levels, if not a linear one. And therefore, wherever you draw the line, you're still going to pick up, there's still going to be weak genotoxins below the ones you detect. So you've got as a summary of the statistical analysis, you've got issues are between pairwise and dose response analyses, contrast between trying to use modeling, which genotox people are not particularly comfortable with, against just statistical significance. There's lots of multiple comparisons issues. And then the argument that what you're producing is a qualitative result, it's a hazard rather than quantitative and is a risk, and you want to get some dichotomous distinction between a positive or a negative, i.e. a genotoxic or non-genotoxic. So the whole assessment is to try to draw a line saying this is genotoxic or thus this is non-genotoxic. And is that based on a statistical test or on some whole difference? And this brings into the argument about statistical significance and biological importance, and the reappearance in the area of no effect levels that have gradually been becoming out of fashion in toxicology in general, this idea that there's some sort of almost threshold point below which there's no effect. And how do you cope with the fact that quite a few of the negatives are probably weak genotoxins, and is that a problem? Okay, so that's sort of left in a somewhat, I guess, the way things are at the moment, somewhat for statistical people, probably somewhat unsatisfactory, but I don't think it's something which is going to change dramatically in the future. It's sort of a feeling that there's some very interesting data, lots of interesting statistics that can be done on them, but actually a very much a fallback on sort of almost non-statistical criteria for making decisions. However, what I want to do now is to move beyond that and to talk about some of the areas where the results of things like the Ames test are being applied, and where there may be some issues and areas where there could be some interesting things for statisticians and statistical input into the discussions. So the first one will be in the use of the Ames test for carcinogenicity prediction. And here, there's at first, when the Ames test first came out, there was people were very enthusiastic because it seemed to be nearly 100% predictive of chemicals that were carcinogens. So the mutagenicity was predicting carcinogenicity at sort of 90%, probably because the most potent chemicals were originally looked at. As time went by, it dropped down to 80, and now the latest one, which is one of the latest ones, which was is in the UK Committee on Mutagenicity guidelines, in the annexes, work by David Kirkland and colleagues, who's saying now that the sensitivity of the Ames test is about 60%, and there's the actual data that was derived down below. So out of 540 chemicals that are which were defined as carcinogens, about 318 were detected by the Ames test as positive using the methods we just talked about. 223 were negative using the cutoffs that were just mentioned. So the Ames test had dropped to around 50–60% sensitivity, and also the issue that it's not everything that is positive is a carcinogen. So there's about 75% specificity. Issues around actually very relatively small amount of non-carcinogens have been tested. So there's an issue around the prevalence of things for the prediction aspect. Part of the reason that the sensitivity is as low as it is that not all the carcinogens, the 540 carcinogens, are likely to be carcinogens because the DNA is damaged. So the Ames test picks up DNA damage, but it doesn't pick up other types of damage which might cause a chemical to be a carcinogen. It does raise a sort of somewhat interesting circularity of an argument that you sometimes see the Ames test being described as extremely good predictor of DNA damaging carcinogens. And then you discover that the criteria for being a DNA damaging carcinogen is often the mechanistic evidence is it's positive in an Ames test. So you have the Ames test predicting itself, not always at quite 100%. So this has generated a lot of work, particularly by people like David Kirkland, who've been producing databases to try and help see whether they can improve the predictivity from short-term tests of rodent carcinogenicity, and this has been supported by the European Commission, ECVAM. They've created a genotoxicity and carcinogenicity database of Ames positive chemicals, and people like David have produced a lot of work to list all the Ames test positive chemicals and their results in other short-term testing, and to look for sort of, are there combinations which can improve prediction? And one potential or one interesting area which is to think about is that for each of these chemicals, let's say acrylamide nitrile, it's a positive. Thinking about the number of number of plates that have been used in the Ames test, you're probably talking about 180, 300, or if there are more than one study, 500 or 600 pieces of data have been reduced down to a positive or a negative. And it may be interesting, it could be very difficult to do, but it might be interesting to see whether there's so many possible meta-analyses could be done to get more, extract more out of that data to see whether that would actually improve the predictivity. The other area where Ames test is quite used a lot is as a sort of measure to see whether some of the in silico methods, the chemical structure methods and expert systems are any good at potentially picking up carcinogenicity without having to do any animal tests. So the potential to sort of assess QSAR predictivity against the Ames test. This springs from work of John Ashby and Ray Tennant, who developed, looked at chemicals and tried to identify parts of the structure, all the red bits on these chemical formulae, which were structural alerts for potential mutagenicity, carcinogenicity. So they produced this sort of hybrid molecule with all of the things on. I don't think anyone could ever manage to manufacture that one on its own, but the indication being that if you have in your structure, if your chemical has one of these subgroups in its structure, it has a higher probability of being a carcinogen or Ames test method. And so various of the QSR people, expert systems, have been trying to sort of validate these models against the Ames test, taking into account what we've already just said about the sort of potential inaccuracies or uncertainties around Ames test data. So this is one just saying that one particular model has got 92% accuracy. Not all of them have that level. Again, the Committee on Mutagenicity did a table looking at various, this is Derek is a sort of expert rule-based system, agreed with 65% agreement with the Ames test positive. These vary from time to time. Another one, TopCat, about 73%. Some of the QSARs, 81%, and so on. So the Ames test here is being used very much as a sort of thing to validate some of the expert systems, if you like, artificial intelligence systems against to give some idea what might be the best for what might be the best system for either replacement of animals or getting indication of chemicals, either which there's not enough chemical available to test as to whether there's a potential problem. Another area which was looked at using the Ames test and spun out of the work that Barry Margolin did was to see whether by measuring the mutation rate in the dose-response relationship, that in any way was correlated or associated with similar measures from carcinogenicity studies. And this sprung out again so there was Barry's model. So looking at the values of B1, the mutation, if you like, the mutation rate as a measure of potency of the dose response slope, could that be used to predict the slope of the carcinogenicity dose response? And initially it looked like it could be. And then John Ashby, I just mentioned before, then at ICI in the late 70s, and Jerry Stiles started to challenge people to say, is it really true that the Ames test potency measure matches the long-term cancer, 2-year cancer biopsy potency measure? And that stimulated work particularly by Walter Pygosh and David Howell over at the National Institute of Environmental Health Sciences, and they did quite a study of 112 compounds that the US National Toxicology Program had tested in long-term cancer bioassays, and they found that there was a positive correlation of about 0.48, but they, as measured by these dose-response relationships, if you like, the betas, but actually that correlation wasn't good enough to really use it as a quantitative predictor of carcinogenic potency. The spread was too wide. Now again, the question raises is this a real consequence of the, if you like, the biological properties of the chemicals, differences between how they respond in the bacteria to how they respond in a rodent, or is it because of some of the uncertainties introduced by how the criteria for defining the chemical as a positive or a negative might come about, or the variability in it? But anyway, that has the potential of using the Ames test for predicting carcinogenic potency has faded, and it's not really taken into account anymore. Another area which where the Ames test has a role, and this is particularly in the case of the pharmaceutical industry, is in the development of what is called a threshold of toxicological concern, particularly for impurities in the manufacturing process, which the chemical process to produce the particular drug, when it's scaled up, may produce a small amounts of various impurities, some of which have in the past been genotoxic, and the concern was, could that mean that the quality of the material isn't good enough? On the other hand, to try and remove them is extremely expensive. Is there some sort of level below which, for practical purposes, there's no real risk? So the concept of the threshold of toxicological concern was developed, and it's an idea that, particularly in the food supply, when you know the chemical structure of the chemical, you know how much the exposure is, but there isn't, you either can't or there isn't toxicological data. Is there a value below which you can be comfortable that there's no appreciable risk to health? And this TTC was built up, as it said in this quote from Microbe, on a statistical analysis, they called it, of toxicological data from a broad range of chemicals, and an extrapolation to an effect which was considered to represent negligible risk in humans. And for the pharmaceutical industry, that was about 1.5 micrograms per person per day is considered to be associated with a negligible risk, which is equivalent to about a theoretical less than 1 in 100,000 lifetime risk of cancer as a result of the exposures. So that was being used as default. And the Ames test, in this case, these are the sort of European Medicine Agency guidance and the latest FDA guidance on mutagenic impurities. And the Ames test here can be used as a test when you've got a structural alert that suggests that the chemical might be a mutagen or genotoxic. The Ames test is used, and if the Ames test is negative, you can go above the TTC. If it's positive, you need to keep below the threshold of toxicological concern. Again, some interesting statistical issues around that development. So that was just a comment from some of the people in the food industry saying, that Ames test often the only data that's available for some of these trace chemicals. How do we bring that into the TTC system? Just want to finish off with a few comments about new topics. At the moment, the OECD wasn't updated in the latest round. The top concentration remains is 5 milligram per plate in absence of cytotoxicity, but they have also talked about some developments to automate and minimize the amount of the test substance. But these haven't yet been universally accepted as replacements for the standard test. And the OECD has a detailed review paper that's part of their process for looking at what are called miniaturized versions of the Ames test. And they've got a work plan which they're working on to see whether these new versions, smaller versions, are used alongside the traditional Ames test. The advantage is that they don't need as much material to conduct the assay. They can use the sort of multi-well, 96-well, 24, 384 plates that are available. They can use a liquid media instead of agar, and they've got high throughput. And it says some of these are now in use for screening, product development or early discovery phase, but not in regulatory use. And so there's some pressure to see whether they could be used. And these are, one of them are the Microbe Ames test, which uses a 24-well plate. It's interesting, and here's the little layout of the plates. It's interesting that actually the secondary plate is 3 replicates are taken from dose 1, dose 2, dose 3, dose 4, put into dose 1, dose 2, dose 3, dose 4. Interesting at this point that go back to the Mahon paper, of 1989, I think it was, who actually talked about in the Ames test randomizing the plates to avoid risks of runs and biases being introduced. And it's interesting that these new versions, there's no evidence of any sort of attempt to randomize the plates or in any way to ensure that there aren't plate-related effects starting to appear. So there may be something there for the statisticians to suggest that these methods could be improved by more statistical thinking into their designs. Similarly, there's one which is called a fluctuation test, which is another version of the Ames test. And here the wells, there are 90, it's a 384 well plate. On the same plate, you have all 6 doses plus the negative and the positive control. 48 wells are seeded with bacteria and the compound. And when the liquid changes from blue to yellow, it indicates the mutations occurred. And it's called a fluctuation test, has been widely used in the past. But these are things coming through. So some discussion points just to finish off, just to close up really. Are the false positives and the false negatives really misleading, or is this failure to predict the result of the biology, or could it be that something to do with the underlying errors and biases that statistics could help with? And similarly, for prediction, have we got a good estimate of the real prevalence? Just mention some of the design issues, particularly in the new versions. There's issues related to quantitative analysis to try and quantitate genetic toxicology data, particularly in some of the in vivo tests. It's unlikely, given the weaknesses with the potency correlation, that that'll come into the Ames test. I've called it meta-analysis, but is there potential for statisticians to get involved in looking at some of these combinations across a lot of studies to see whether there's more that could be got out of them? In general, more statistical input into the existing assays, but also the new ones. Perhaps things like PSI, stats, Tox group could actually put things into OECD revisions when they come out for review. It may be something where statisticians from the pharmaceutical industry could actually have an impact. Right, I think this is just as a concluding remark. I just go back really to the Ames test. It's 1973 it was born. I just looked to see what was around in 1974. A man called Steve Jobs had just begun working at Atari. The Intel 8080, which is apparently the sort of workhorse over which most of the chips that are in Windows-based computers are still based upon, was first produced. And I did like the fact that you could start to build your own personal mini computer. So I think the Ames test it's middle-aged. It's still alive and thriving, but it's getting a bit fixed in its ways. I think for statisticians, it's a mature test. There's a lot of expert that's subject to decision making, but that's not going to change, I don't think. There is a statistical component, but it has a limited influence upon these, if you like, the expert judgment. There's probably minimal scope for innovation in the future. What are the opportunities, though? I think there's application of the there's an opportunity for statisticians to look at how if you like, the meta-analysis of these studies is being applied to the biology. So there's potential to look at that, and there's potential for the statistical thinking in these sort of meta-analyses, in this idea of how to develop batteries of tests and such like. And finally, I think that the new versions would benefit from interactions with the statisticians. So I think I'll stop at that point.
Thanks a lot, David, for your great presentation. I think we have time for a few questions. And I can start. You already said that QSAR models are validated against the Ames test. What is your expectation with respect to the future of the Ames test in general? I mean, there is a certain competition to in silico strategies, and this may yield a lower amount of tests in the future. Is that what you expect?
I think there'll be some pressure for these newer methods to replace the existing one. They're going to be cheaper, at least whether they're cheaper, but they're probably quicker and easier to do. They may have a lot of benefit for people who are doing this threshold of toxicological concern, because you don't need much chemical, and you just need a positive or negative result, however that might be termed in these tests, to say, okay, it's a genotoxin, therefore you've got to keep it below 1.5 micrograms, or alternatively, it's not a genotoxin, you can go above it. So I think that's probably one of the developments. I think most chemicals that are going to go through REACH and all those sorts of processes, certainly in the short to medium term, are going to have an Ames test.
Okay. Second question is...
I'll finish off. I think there is some steam behind... well, no, there is some people beginning to say some of these results are not right. They were badly done. They were not correctly interpreted. We need to go back and reassess them. That might be where some statisticians could get involved and start, saying, well, actually, what is your algorithm?
Okay, I got another question, and I will read it in the chat box. David.
This is the batteries.
Sorry?
This is the question about batteries of different tests.
Right.
Yeah. This has been going around ever since, I think, the 1980s. Could there be some combination of tests which would be the better prediction than Ames? Well, to some extent, there already is one. I mean, there is the standard in vitro tests are the Ames test and the in vitro micronucleus or chromosome aberration, or sometimes a mouse lymphoma assay, because they are aimed at picking up 3 different types of genetic damage: mutations, chromosomal damage, and chromosomal the loss of chromosomes. So they're aimed at slightly different endpoints. They form pretty well most of the sort of standard battery. And then you might go into the in vivo tests. There's a bit of a debate in the field about when you do in vivo testing, when you bring the mouse tests in. The Committee on Mutagenicity said you should be doing the in vitro tests first and then move on to an in vivo test if you really have to. Some other people say, well, the in vivo micronucleus test should be done fairly early on, irrespective of what others are used. Most of the other mutagenicity tests, and there were probably about 100 at the end of the 80s, have fallen by the wayside. There are some new ones beginning to come through, which are aimed more at being cheap or easy to use, or different endpoints. But there's going to be it takes a long time to introduce a new test. The OECD guidelines, you see, the one for the Ames was 1997. They might get round to revising it in the next 3 or 4 years, possibly. There's only been about 2 or 3 new ones introduced. The micro Ames and the other Ames test, the mini Ames 2, sorry, have been around for 10, 15, 20 years, and only now are just beginning to get the possibility of getting an OECD guideline.
With respect to these test batteries, are there any recommendable statistical strategies or ideas for analyzing different tests within one test battery under one hat? For example, as you mentioned, the Ames test, the micronucleus test, the whatever commit assay.
There have been various attempts to if you like, do sort of the equivalent of logistic regression on, which combinations give the best prediction of these tests. The trouble I think they run into is that from the genetic toxicologist point of view, the Ames test is there to identify essentially point mutations, changes in bases or small changes, whereas the in vitro micronucleus is there to see big breaks in chromosomes or losses of chromosomes. So they're doing different things. In that sense, they're supposedly complementary to one another. And then there's always the issue about what about the ones which were both or three tests miss, but apparently are still carcinogens. Until you know more about the mechanism for those carcinogens, you probably can't identify which is the best test to have predicted them.
David, with regard to the twofold discussion that you brought up earlier and putting your statistical results in relation to your biological relevance, what about historical controls? To what extent do you believe they can help there?
Well, it's increasingly in some of the newer ones, like the micronucleus tests, the idea is to try and use the historical control to get some sort of feel for the spread of data that the lab that the lab may produce, and then to look to see whether, provided that the concurrent control is well within that band, or what do you want to call it, interval. If you're then going outside it and you're treated, then that's probably good evidence that you've got something that's biologically happening. To give some degree of quantification of the uncertainties around things. Obviously, the negative control is the primary control for the comparisons, but the historical control does give you some feeling for whether what you're seeing is a large effect or a relatively small effect.
Exactly.
And also, the other aspect is that it does give some idea, if you've got a lot of historical control data and you can present it in quality control ways, it does give the assessor some confidence that you're either good at the test, you know how to do it, and therefore can keep within a pretty reasonable boundaries. Or you actually are changing dramatically, or 6 months ago, your historical control changed dramatically. I mean, the one thing is to try to get around is for the fact that your historical range is going to get wider and wider the longer you're doing the study. And some people have tried to say, oh, our data is within the historical range, therefore it's normal. But in fact, if you think about it, the historical range just gets wider and wider the more you do.
I'm so sorry, but we are running a little bit out of time. I think we have time for one more short question.
I only maybe have a comment on the last question, if there is time.
Go ahead, Bastian.
Yeah, so it's related to the twofold increase versus the effects that are going outside of the historical data. So I did an analysis on one of the strains, TA98, where we collected the data of positive results in the strain. And then we really found that if you go above the twofold, that in each case you also go outside of the historical data. So this was at least something that I think would help to say more about the biological relevance.
Yes. Yeah, I wonder why it's not used a little bit more often also, or why it's not advocated a little bit more, but okay.
Yeah, but you're completely right. It's now implemented in the other genotoxicity assays, like the micronucleus test and the others. So I would think it's at least an evaluation that could be done.
Yes, I agree. Yeah. And also the monitoring aspect, I think it's still important, like David mentioned earlier. In addition to that, you do take some variability into account, so it's not like an ad hoc twofold, something like that. And you can put your statistical results into perspective, so to speak. So, yeah.
I think the one thing that comes over is that if you like, the algorithm or the criteria for these positives and negatives that appear in the various databases are different from study to study.
Yeah.
I think that may well be that some of the people who are collecting the data will start saying, are we sure now that everything we say is positive using the criteria for some of them is the same as using another criteria? So they may want to reevaluate some of them again.
Yeah.
Okay, I'm so sorry again, but I think it's 3 o'clock in Britain and 4 o'clock in the rest of Europe. So I think we have to close our webinar. I would like to express my sincere thanks to David Lavelle for his work and for this great presentation, and to the audience for your participation. And we hope everybody enjoyed this webinar. And we will meet again on the 12th of December when Thomas Yaki, Professor in Lancaster, is presenting on optimal design for microsampling. So thanks a lot, and bye-bye to everybody.
Thank you, Ben. Goodbye.
Bye-bye.
Bye-bye. Thank you.
Goodbye.